Okay, so we were just beginning to look at this second optimization problem. We decided that the quantity that we're trying to minimize here is distance, right? So our objective function is going to be some kind of a distance function, okay? The only picture that would make any sense for us to look at, if anything, is just maybe, is just this. We've got this graph of our function. This is a graph of the function f of x equals 4 minus x squared. And what would I call my variables here? The coordinates of this point are 0, 2. I'm trying to find the nearest point. I don't know where it is. I'm trying to find the nearest point on the graph to the yellow point. What are my variables going to be? What do you think? You can type it in chat if you want. Okay. X and Y. Yeah, that makes sense, wouldn't it? X and Y are going to be the coordinates of the red point. And so if I wanted to come up with a distance function, the blue line represents the distance, right? Okay, how can I come up with a distance function? If I'm calling the distance, let's call the distance S. What's my equation then? And maybe I'll make this part of the picture a little bit bigger. Right, so I've got this point with coordinates 0, 2. And I've got this other point up here with coordinates x, y. And here's what I'm looking for. Here's my distance, S. How do I define S in terms of x and y?
One of the points and then 0 and 2 for the other point.
Okay, so the distance formula is really just the Pythagorean theorem, right? So if that's S, that's like the hypotenuse of my triangle. The base of the triangle is just going to be the difference in the x coordinates. So this one is 0, this one is x. So what is that distance then? What's the length of the base? Just x, right? X minus 0 is the same as x. So that's x. What's going to be the length of the height here?
Y minus 2.
Everybody agree? Y minus 2. This y value is 2. This y value is y. And so the distance between those is just y minus 2. So the distance formula would have us say that S is equal to the square root of x squared plus the quantity y minus 2 squared, right? Everybody agree? Okay, so we've got S as a function of two variables. So that's kind of a problem, right? We need to be able to write those in terms of a single variable. Let's do that first. There's two things I want to get to here. Do I have a substitution equation? What do you think? Let's see. Andrew, do I have a substitution equation there that I can make? Because I want to be able to get my distance as a function of just one variable, either s as a function of x or y. Yeah, we can, right? Because look what we have up here. We have our definition of f of x. Well, that's the same thing as saying y, isn't it? F of x is just y. So we've got this equation, y equals 4 minus x squared. There's my substitution equation, right? I can pop that in for y, and we get s equals the square root of x squared plus y, which is 4 minus x squared minus 2, that whole thing squared, right? And I could simplify that. Four minus x squared is going to be what? Well, I'm going to get 4 squared minus 2 times 4 times x squared. So 16 minus 8x squared plus x squared squared. And then I've got my minus, oh, whoops, you know what I did there? I messed that up. I squared the wrong thing. We've got y minus 2 that's being squared. So that's 4 minus x squared minus 2. What's that? What does that all work out to be? 4 minus x squared minus 2 is what? Two minus x squared. Good. Everybody agree? Just combining like terms. So I get 2 minus x squared quantity squared. And we know, remember, we know that a minus b squared is just a squared minus 2ab plus b squared, right? So then this would just equal x squared plus, if I FOIL that whole thing out, I'm going to get 4 minus 4x squared plus x to the fourth. I could combine my like terms. X squared minus 4x squared is a minus 3x squared. And so I end up with my distance function equals the square root of x to the fourth minus 3x squared plus 4. Everybody agree? And look, now that's s of x. So that's pretty good. Everybody agree? Give me 1 to 5 on that. Is that all good? Okay. Okay, now what are they asking for here? They want to know which, what are the coordinates of the point or points that are closest to 0, 2. Okay. They don't really want to know what the distance is. They just want to know the points that are closest. So for us, that's going to mean we want to minimize s and find the value of the input x that causes the distance function to be minimized, right? Okay, does that function look like a very fun one to differentiate? And if not, how come? What makes it ugly? Okay, the square root does, right? It's not impossible to do, but it makes it much more difficult. And after we differentiate it, isn't that going to make it a little bit harder to find critical numbers? You know, we could do it, but it makes it more complex. So can anybody think of a trick that we could pull here? Is there a different function maybe that we could choose that's going to give us the same answer? Because we just want to know what's the x value that minimizes the distance. Look at that triangle, right? What does the Pythagorean theorem tell us? Pythagorean theorem tells us that leg squared plus leg squared equals hypotenuse squared, right? So if I just apply the Pythagorean theorem, and you don't have to do it this way. I don't even think the published solutions do it this way, but this is just a pretty cool way to do it, a better way to do it that I'm going to show you. If we just apply the Pythagorean theorem directly, what's that give us from that triangle? We get s squared equals x squared plus the quantity y minus 2 squared, okay? Well, we already know if we plug y in, all of this stuff right here, that was just everything that's inside the radical, right? So that all just ends up being this. So we get s squared equals x to the fourth minus 3x squared plus 4. Well, wouldn't the square of the distance also be minimized when the distance is minimized? True or false? Does that statement make sense? That's true. That's a true statement, isn't it? Right? If the distance is minimized, then the square of the distance would also be minimized. Okay, so why not do this? Why not, instead of having this complicated distance function, let's just pick an easier function. Let's just pick the function, we're going to call it f of x, for example. And it's just distance squared. But the minimum of f of x has to correspond to the minimum of s of x. And so why not solve the easier of the two problems if they're going to give us the same solution? What a great trick. We do that in math frequently, if we can. Okay? Give me a 1 to 5 on that concept. Does that make sense, the trick that we're employing here? Okay. Okay. I mean, did we have to do that? No. We could have done it the other way. We would have ended up getting the same answer, but this is going to be a lot easier. When we do the derivatives now, look how simple they are. This is just a polynomial. So we're just going to get 4x cubed minus 6x, right? That's it. That's our first derivative. Our second derivative is just going to be 12x squared minus 6. Okay, so then where is our first derivative if we factor it? I could factor out a 2x, leaving me with 2x squared minus 3, right? So then what can we say about our critical numbers? The first derivative is obviously nowhere undefined, but it's equal to 0 at x equals 0, right? Or x equals plus or minus the square root of 3/2. Everybody agree? If I set that equal to 0 and add 3 to the other side, divide by 2 and square root. Everybody agree? Okay? So now let's go to our table. We need to know the domain though. What values would make sense here for our domain if we're calculating a distance? There's a couple ways we could do this. What would make sense for my domain? Okay, we could just do all reals, couldn't we? Right, because the point could be any place on that function. Everybody agree? Right. The point. Imagine that this parabola is just a piece of wire that forms this infinite parabolic shape, and the point is just a bead sliding on that infinite bent piece of wire. Right. The bead could go anywhere. It could have any x value, couldn't it? Okay. So our domain, we could say, is, and we'll come back to this in a second, and we'll ask, okay, was there another way we could have done this too? But we could just say that our domain goes from negative infinity to infinity, right? Okay, what are our critical numbers? Well, we had critical numbers at negative square root of 3/2, 0, and positive the square root of 3/2. Those were zeros of my first derivative. Oh, and this is not y. What should I have in my next row here? Y is it's kind of a poor choice because y is a coordinate this time. What should I have in my second row? Okay, S would be distance. You're right. And that's a good answer, except we didn't actually use distance. What did we use? If I scroll down here, I just arbitrarily called it S or F, right? Because it was this, we actually used the square of distance, right? Everybody agree? Okay. I could have used distance, it's just harder derivatives. So we had F prime, and F double prime. And we calculated these critical numbers were the zeros of our first derivative. So we know they produce horizontal tangents. Now we can the second derivative was easy. So all we have to do is just determine what's the sign of the second derivative at each of these places. Okay, so if I choose plus or minus the square root of 3/2. Okay, if I plug that in, I'm going to get a positive result, aren't I? Because I'm going to get, when I square the square root of 3/2, I get 3/2. 12 times 3/2 is a lot bigger than 6. So I'm getting positive second derivatives here and here. And if I plug 0 in for x, I'm getting -6. So I'm getting a negative second derivative there. So what's that telling me then? Well, these are minima, and that's a local maximum, right? Does that make sense? Okay, so if we thought about the graph of this, everybody give me a 1 to 5 on those, the table there. Okay. Okay. So if I had to make a little sketch of this thing then, and we could plug values in for f if we wanted to, but we don't even really need to. If I wanted to make a little sketch of this, what's it going to look like? I'm going to take a picture and go to the next page. Okay, what's that have to produce? So here's x equals 0. So that's the y-axis. Come on. There we go. I've got a local maximum here, and I've got local minima here, and those are the only extrema because I only had 3 critical numbers. So can this thing ever turn down to the left of this negative critical number? Can the function ever turn down again? Yes or no? Give me a y or an n. Okay, that's correct. It can't. How come? How come it can't, Madeline, how come it can't turn down ever again? That's a correct statement. So if I start to graph this thing, the graph's gonna look like, it's gonna look like this, right? I've got this maximum, I get a minimum, and then everybody's correctly telling me that this thing can never do that again. It can't ever turn down again. How come? What's your logic on that one? Question was for Madeline. I don't know if she heard it or not.
Okay, sorry, my thing's really bad.
Well, that's all right.
Is it because there are no more critical numbers?
Exactly. That's it. Exactly. There's no more critical numbers. And so in order to turn down, there would have to be another critical number, wouldn't there? Yeah. Good. And then same thing on the other side, right? It's going to go down to this minimum that we get, and then it goes back up again forever. So could we have, I don't want to spend too much time on this, but it's kind of fun just to plumb the depths of these problems. What's the symmetry of this function that we developed? If we look down at this function, here's my function, right, f of x. Does it have symmetry, odd or even symmetry? Yeah, it's even, isn't it? Right, we can see that that's going to be even symmetry. It's a polynomial with only even exponents, 4, 2, and 0, right? 4 times x to the 0. So we know that this thing would have to have symmetry about the y-axis, and so every feature I get to the right is going to be reflected to the left, right? Okay, and so we end up with two places where where the distance is minimized. The question asks for, I think, the coordinates, right? It wants the point. So I calculated the x coordinates of the points. How would I find the y coordinates? And I even put a box around it for you because it was my substitution equation, right? We always do that. Plug it in, right? Yeah, I'm just going to go plug into my function that defines the shape, right? That's the function that links x's and y's, right? So then we would just get, in both of those cases, y would be equal to 4 minus, either one, whichever one I put in, I'm going to get the same result back, aren't I? I'm going to get minus, plus or minus the square root of 3 halves squared just gives me 3 halves. 4 minus 3 halves is what, 5 halves? Or, yeah. So I'm going to get the 2 points, negative square root of 3 over 2, 5 halves, and positive the square root of 3 over 2. Oh, no, that's wrong. It's not, we don't want f, right? We want y. So I can't put it into the table, right? This is different, right? We're just wanting the locations of the points on the curve. So my 2 points would be, run out of colors here. My 2 points would be negative square root of 3 over 2, all inside the radical, 5 halves, and positive square root of 3 halves, 5/2. Okay? Good? Give me 1 to 5 on that. Okay. Okay, I'm going to show a little mercy here and call her quits for today. We finished up that example. I think that's pretty good. So there will be an assignment that will be opening up here soon. I'm trying to get it done right now. I just want to make sure I want to pick the fewest number of problems that I feel like will be adequate. So I'm still just debating on a couple problems. I got to make a decision, but I'll put it up here within, an hour or so. It should be up. Okay. All right. Have a good one. Go enjoy the sunshine. I will see you in a couple days. You too, Kirsten. Have a good day. Bye, Seth.